In 2018, MIT's Plasma Science and Fusion Center spun out a business called Quaise, specifically focused on ultra-deep geothermal using fusion tech hybrid systems that combine traditional rotary drilling with gyrotron-powered millimeter wave technology, while pumping in argon as a purge gas to clean and cool the bore while firing rock particles back up to the surface and out of the way. The company has raised some $63 million to date, comprising $18 million in seed funding, $5 million in grants, and $40 million in a series of financing round closed earlier this month. Quaise plans to drill holes up to 20 kilometers deep, significantly deeper than the actual deepest hole, where the team took nearly 20 years to reach the limit. Quaise expects its gyrotron-enhanced process to take just 100 days. At about 20 kilometers depth, Quaise expects to find temperatures around 500 degrees Celsius, which is well past the point where geothermal energy takes a massive leap in efficiency. Quaise is working on full-scale, field-deployable demonstration machines, which it says will begin operating in 2024. It plans to have its first super-hot enhanced geothermal system rated to 100 megawatts in operation by 2026. Quaise expects to repower its first fossil-fired plant in 2028, and then go on to refine and replicate the process all over the world, since the heat should be available absolutely anywhere on Earth with this drilling technology. There are somewhere upwards of 8,500 coal-fired power plants around the world, totaling over 2,000 gigawatts of capacity, and they'll all have to find something else to do by 2050, so the opportunity is clearly mammoth. Everyone knows the Earth's core is hot, but maybe the scale of it still has the power to surprise. Temperatures in the iron center of the core are estimated to be around 5,200 degrees Celsius, generated by heat from radioactive elements decaying combining with heat that still remains from the very formation of the planet, an event of cataclysmic violence when a swirling cloud of gas and dust was crushed into a ball by its own gravity. Where there's access to heat, there's harvestable geothermal energy. And there's so much heat below the Earth's surface, that tapping just 0.1% of it could supply the entire world's energy needs for more than 20 million years. The problem is access. The actual deepest holes in human history are not deep enough. If we could drill deep enough, we could put geothermal power stations just about anywhere we wanted them. Where conditions become too difficult for physical drill bits to operate, researchers have been testing the capabilities of directed energy beams to heat, melt, fracture and even vaporize basement rock in a process called spallation, before the drill head even touches it. A direct energy drill would effectively cauterize the rock it cut through, melting the bore shaft as it goes and vitrifying it into a glassy layer that would seal out fluids, gases and other contaminants that have caused problems in previous ultra-deep drilling projects. Such a solution might come from the world of nuclear fusion. In order to replicate the conditions that smash atoms together at the heart of the sun, and thus release the safest and cleanest form of nuclear energy, fusion researchers need to generate staggering amounts of heat. We're talking in the range of a sustained 150 million degrees, in the case of the ITER fusion reactor, the world's largest fusion experiment. One example is the gyrotron. Gyrotrons generate electromagnetic waves in the millimeter wave part of the spectrum, with wavelengths shorter than microwaves, but longer than visible or infrared light. Indeed, gyrotrons capable of generating continuous energy beams over a megawatt in power are now becoming available, and that's amazing news for deep drillers. That would be a huge boost to traditional oil and gas drilling projects, but, barring too many further surprises, it should also significantly change the equation for ultra-deep drilling, making it possible and profitable to get deep enough into the crust to unlock some of the Earth's immense geothermal energy potential. This would be a massive shift that could be for baseline clean energy and the process of decarbonization. If this technology works as expected, and the economics stack up, this new use for gyrotrons could ironically end up putting fusion reactors out of a job. Importantly, it'll take up almost no space on the surface, in contrast to industrial-scale solar and wind. It'll also precipitate a global geopolitical shift, since every country will have equal access to its own virtually inexhaustible energy source, and it sure will be nice when big countries don't have to liberate the populations of smaller ones to gain access to energy resources.